frequency constant, we have to vary the rotor resistance, right? How to vary the rotor resistance? We can add some resistance externally to the rotor. So this rotor side speed control method or the rotor resistance speed control method is applicable only for slip ring induction motor, because in slip ring induction motor only we have the provision to add external resistance to the rotor. So if you add external resistance to the rotor, if you draw the torque slip characteristics for various values of R, so R2 is the actual rotor resistance and R2 dash is the increased rotor resistance, and R2 double dash further increased rotor resistance. So R2 is lesser than R2 dash, lesser than R2 double dash. So if you draw the torque slip characteristics, the torque slip characteristics already we have seen in unit 1 as effect of rotor resistance variation in torque speed characteristics. So similar graph only we will get it, and how we can say the speed is controlled or the speed is varied. So you can understand by the load torque. So as usual, we have taken the constant load torque TL, and the intersection of load torque with the machine torque is the operating point. And from the graph we can understand that for the resistance R2, the operating speed is N1, and for the resistance R2 dash, the operating speed is N2. For the resistance R2 double dash, the operating speed is N3. So from this we can understand that when we vary the rotor resistance, the speed can be varied. Right? So N1 is greater than N2, that is greater than N3. So this is the rotor resistance speed control method. And how to vary the rotor resistance? By adding some rheostat to the rotor. Right? So we will take this small problem in rotor resistance speed control method. The problem goes like this. A 4-pole 50 Hz 3-phase induction motor has rotor resistance of 0.2 ohm per phase and rotor standstill reactance of 1 ohm per phase. On full load, it is running with a slip of 4%. Calculate the extra resistance required in the rotor circuit per phase to reduce the speed to 1260 rpm on the same load. So here they are taking the load torque is constant. That is the meaning of same load. First, as usual, you write the given data. So I have written the given data. P is equal to 4, F is equal to 50 Hz. You can see here, P is equal to 4, F is equal to 50 Hz. Rotor resistance is 0.2 ohm per phase. Rotor reactance is 1 ohm per phase, and slip is 4%. Right? So now what they are asking is that what should be the external rotor resistance to be added in the rotor section so that the speed of the motor will be 1260 rpm. If I want to run the machine at the speed of 1260 rpm, what is the extra resistance to be added in the rotor circuit? So that is what they are asking. So they are adding some resistance to the already existing resistance R2. So R2 I know that is 0.2 ohm per phase. So now we have to find this R2 external. So the addition of R2 plus R2 external is taken as R2 dash. So this is what they are asking. Right? So for that, first you find the rated speed of the motor. Right? For the rotor resistance 0.2 ohm per phase, what is the speed of the rotor? That you can find using this rotor formula. So NR1 It is the rotor speed corresponding to the rotor resistance 0.2 ohm per phase. That I am taking it as NR1. NR1 is the rotor speed corresponding to 0.2 ohm per phase. So that is equal to 1 minus S into 120 F by P. So what is the rated slip they have given here? The rated slip, it is given as 4%. So you substitute here percentage. So 4 by 100, 120, frequency is 50, number of pole is 4. So your NR1 comes to be 1440 RPM. So this is the rotor speed corresponding to the rotor resistance 0.2 ohm per phase. Now what they are asking is that if you add some resistance externally to already existing rotor resistance, so that is taken as R2 dash. So corresponding to this R2 dash, what would be the rotor external? For that you have to take the condition. The condition is the load torque for the rotor resistance 0.2 ohm per phase, and for the resistance which is added to the already existing resistance, both it is same, because here they are saying same load. Because here they are saying same load. If you want to represent this in the torque speed graph, so you can take the torque speed graph like this, and for the nominal rotor resistance, this is my R2, that is 0.2 ohm per phase. So if you add some resistance externally to the already existing rotor resistance, so my graph will come here. So here they are saying the load torque is constant. The load torque is, that is the meaning. So this is the point NR1, that is 1440 RPM, and this is the point they have given 1260. To get 1260 RPM, what would be R2 double dash? If you find R2 double dash, already know R2, so you can find R2 external easily. So for that, you have to take this condition. Load torque on both the condition are same. So TL1, that is the load torque corresponding to the rotor resistance 0.2. TL2, that is the load torque corresponding to the rotor resistance R2 double dash. Right? R2 dash. Sorry, R2 dash. So what is the load torque equation? Slip V squared R2 by R2 squared plus Sx2 the whole square. So for the rotor resistance 0.2, we are taking slip as S1, and that is equal to K S2 V R2 dash. Now the rotor resistance is increased to R2 dash. So R2 dash it is taken here plus S2 X2 the whole square. So now you have to equate these two equations. So constant of proportionality is same, that is cancelled on both the sides. So V and R2 is known, X2 is known, S1 already it is given 4%. S2 only we have to find out. S2 we can find from the given speed. The given rotor speed is 1260. So synchronous speed is 1500. So if you subtract 1260 from 1500, you will get the slip as 0.16 corresponding to 1260 RPM, that is corresponding to your R2 dash. So when you solve this equation, you will get R2 dash. So R2 dash, it is coming as a quadratic equation. If you solve this equation now, you will get quadratic equation. R2 is having two values. R2 dash is having two values. One is 0.8, another one is 0.032. So if you have to solve this equation. So this equation no, you have to solve. If you solve this equation no, it becomes quadratic equation because you have the square term. So two values of slip you will get. So two values of slip you will get if you solve the quadratic equation. So you will get 0.8 one value and 0.032 as another value, right? So this value we have to take. See, already the nominal rotor resistance is 0.2 ohm per phase. You are adding some external resistance. So definitely your R2 dash, it cannot be 0.02 ohm per phase. It should be 0.8 ohm per phase because that is greater than your 0.2 ohm per phase. And if you substitute 0.8 here, you have to substitute 0.8 here, and R2 already I know it is 0.2. So the external resistance is 0.6 ohm per phase. So if you add 0.6 ohm, if you add 0.6 ohm to already existing resistance with 0.2 ohm, then the rotor speed will come to 1260 rpm from 1440 rpm. If you want, you can draw the torque slip characteristic and you can mark everything. So here your R2 dash, here your R2 dash is 0.8 ohm per phase. So external resistance is 0.6 ohm per phase. Okay. Any doubt in this? So like this, you may get problem in the examination. Sometimes no, I may give constant load torque like this. Sometimes I may give some load torque equation in the examination, right? Equation means you have to find all the values and you have to substitute, that's all. So this is what the solution, just I have written here. So this is all about your rotor resistance speed control method. So what is the advantage in this is that somewhat wide speed control range you will get here, because the what I can say here, your graph, no, it is shifting towards like this. When you add the rotor resistance, the graph, no, it is shifting from this direction to this direction. The maximum torque remains the same and the graph is shifting like this. So because of this, the speed control range somewhat wider you will get when compared to stator voltage control method, but not as much as wider you will get when compared to frequency control method and V/F control method. This is somewhat compromised method to get wide speed control range between V control and F and V/F control. So that is the property of this rotor resistance speed control method. But what is the disadvantage in this? Since you are adding some resistance in the rotor circuit, copper loss will increase. That will reduce the efficiency of the motor. Or unnecessarily, no, the power which is available in the rotor circuit, no, unnecessarily, no, you will be wasting as copper loss, right? So whatever the power which is available in the rotor, simply, no, you are wasting that power in the external resistance. So instead of wasting the rotor power in the external resistance, you can take that power, again you can fed back to the transmission line. So that is called as split power recovery scheme. You see here, so instead of wasting the power in the rotor, you can take that power, again you can fed back to the supply line. So see here, instead of wasting the slip power, whatever the power which is available in the rotor, no, that is called as slip power. A better approach is to convert into AC line power and return it back to line, and rotor speed also can be controlled. See, the rotor resistance is varied, and the power which is wasted in the rotor, that can be utilized. Again, it can be fed back to the transmission line. This can be done using power electronics converter. So not much details are required for you at this level. Just you understand the concept alone. Instead of wasting the rotor power in the rotor circuit, you can take that power, again you can fed back into the grid or transmission line. So this is the block diagram. You see here, you have the transmission line RYB phase. So you have three phases. This is R, this is Y, this is B. So three-phase input is given to the stator of spring induction motor, and this is my rotor. So from the rotor, you are tapping the power, and that power is again fed back to the transmission line, right? So the rotor power is taken from the rotor, and it is again fed back to the supply line using power electronic converter, right? Of course, if there exists voltage difference between the transmission line, suppose this is the voltage V1, this is the voltage V2, because the rotor power, it will be little lesser when compared to the stator power. So always your V2 will be lesser than V1. So V2 will be lesser than V1. So in order to match V1 with V2, we are using some transformer to boost up the voltage. Sometimes transformer is required to boost up the voltage. So the power electronics converters are used to vary the slip, and hence the speed also can be varied. So here two objectives are achieved. One objective is the power is not wasted in the rotor circuit, it is fed back to the transmission line. And another objective is the slip of the rotor is varied and the speed can be controlled. So the both objectives are done, or both the objectives are achieved using power electronics converter. So slip power is processed into the power electronics converter. That is what? To step up the rotor voltage to match with the supply voltage, transformer is used. This speed control method is applicable only for slip spring induction motor. Any doubt in this? Any doubt? Only conceptual way of understanding it is sufficient at this level, because power electronics you do not know. So when you read power electronics, this you can understand how the power is taken, how it is processed, how the power is fed back to the transmission line. Same day, how the speed is controlled. Everything, you can understand after studying the power electronics. So at this level, concept is sufficient. Power electronics converter is used to process all these actions. So that is sufficient. So what is the popular method used in industry? V/S control method is very popularly used in industry. That is the stator side control method, right? So stator side control method, which is popularly used, V/S control method, right? So V/S control method only is very much popularly used with respect to the stator side. With respect to rotor side, slip power recovery scheme is popularly used, right? So out of many speed control methods, V/S control method and slip power recovery scheme both are popularly used in industries. So with this, speed control method in induction motor is completed. Next class, we will start braking of induction motor. Braking already we studied in DC motor. How many types of braking are there? Dynamic or rheostatic braking, plugging, and regenerative braking. So these three braking are also applicable in induction motor, and we will see how it is affecting on the torque slip characteristics and how to achieve that. So all those things we will continue in the next class. Maybe 99% you won't be having any classes from 1st to 7th onwards during your journey period. Anyway, I will discuss with higher authority and I will update the information. Okay. So any doubt, anything you have, you can ask me. Maybe after a week only, I think we'll be able to start the next topic in Unit 2, that is braking of induction motor. So this braking is bending and induction generator is there, and some concept cogging and crawling. 3 topics are there in unit 2, so that I can complete as you come back to the campus. So for your assessment 1, first 2 units will be there. You be ready for that. Okay. I think your assessment is starting from February 21, March 21 onwards, no? Assessment 1?
Yes, sir.
Yeah. So for assessment 1, first 2 units, the induction mission complete you will have. Anyway, I will give this PPT to you. You can refer this PPT. Any doubt at any point of time, if you have, always you can approach me. Thank you all.